Okay. Hello, thank you so much for inviting me to give a talk here. I'm excited to talk to you about our recent work from this March with Alec Petroria Sanjay Raman on the non-BPS path to the string lamppost. I believe I have 25 minutes or something, so I will try to give you a little bit of an overview of the idea of our paper. And please ask me questions during or after. Okay, oops, how do I go? Here. Okay, so the way I'm going to start the Swampland program, where a lot of you are familiar with, and we're trying to sort of understand the what makes an apparently consistent low energy QFT consistent when coupled to gravity. The theories that are consistent, we would say that they belong to the landscape, and those that are not in the swampland. But what is really important is to really be able to understand conditions that lets us make these decisions on what really belongs in the swampland. So what are those conditions? How do we find them? And usually what evidence exists to support our conclusions? So this is part of a very big program, and I will not go into detail, but there's a lot of things that are more widely accepted, like no global symmetries, or maybe even the weak-gravity conjecture. So there are there are many principles with various level of support, and what is after? Oh yeah, okay. A lot of the ideas we have about these conditions or constraints, a lot of them come from string theory. String theory is a nice theory of quantum gravity where we have a lot of tools we understand better. And sometimes by looking at that, we get certain conclusions about what should quantum gravity sort of look like. And we've tried to provide also evidence to support this. So, I mean, a general question is how big part of the quantum gravity landscape is really the string theory landscape? And this is very important because not only about the specific of the theory, but even for the principles we talk about, to be able to really understand whether we are under this lamppost, which is really the string lamppost of trying to say certain general concepts about quantum gravity with only looking at string theory. This is something that we want to avoid bottom-up explanations for the different conjectures or conditions that we think are true. So we want to avoid being in the lamppost. So this is the string lamppost principles, which I'm going to basically be describing. Now, there's many ways to ask these kind of questions, and probably the easiest way to try to understand this landscape would be to just start by the simplest examples possible. This is 32 supercharges. Supersymmetry is very constraining. You can just look at the massless spectrum, for example, of the theory, and then you realize that the supergravity is sort of unique, that you don't have that much choice, and all of them have a UV completeness in string theory. I wouldn't necessarily call this as evidence for the string for completeness of the string lamppost, but at least in this case, we have a grasp of the relation. Now, of course, as you go down in supercharges, supersymmetry is less restrictive, you have more choices. So even if you go to the next interesting case, like 16 supercharges, you have a lot of choice. So you could, in principle, have infinitely many vector multiplets in your theory, different types of gauge groups. There's nothing in principle except certain anomalies restricting you. But we know, at least from string theory, that this is not the case. There's only like finitely many possibilities. Like even in 10 dimensions, there you know the dimensions. For example, 90. There's 3 ranks available, 80 similar, and 70 few more. But it's both bounded and specific types only exist. So you could answer this, you could ask this question, is this a universal principle, or is it are we in the string lamppost again? Now, in 19, we showed that the rank is in fact bounded by using certain Swampland principles, and it has to be bounded by 26 minus d. So at least this tells us that the infinitely many possibilities are actually in fact finite, that are consistent. So now you can put this all in a kind of a bigger table based on supercharges and dimension, and sort of look at the possibilities, both in terms of gauge groups. For example, in 8 dimensions, certain gauge groups are not allowed in string theory. The ranks, the patterns you see, how, for example, universal F-theory compactifications could be. This is at least a large class of these, etc. So the point is, how much of this can we reproduce from bottom up? Well, there's been a lot of work outside just our bound, but that people have been able to specify why, for example, this patterns exists like this, why, for example, these gauge groups are not allowed even from bottom up, and to introduce more and more conditions to try to understand the low energy spectrum. So at least for certain dimensions, if you ask me whether we understand the landscape, possible consistent landscape using transform principles, it seems pretty much complete. Although there's much more things that define a theory other than this, including massless spectrum, moduli space, and possible enhancements, and many other things. So I would say that today we're going to be focusing on 9 dimensions and 16 supercharges, and which we already know the possible ranks and the possible enhancement because of this paper here. But what we're going to try to understand is different parts of the moduli space. So focus on non-BPS limits, which I'm going to be defining later on. But a lot of aspects that we see that are interesting in string theory is that at infinite distances, weird things happen. New physics comes up, dualities occur. So there is a very nice web of dualities connecting different aspects of the moduli space of a theory. And we sort of believe that this is a more general principle of quantum gravity. And we encode this belief in some different conjectures. For example, the most basic, the distance conjecture, which tells us that in a quantum gravity, if you go at large excursions in expectation value of some massless field, then you expect a light tower with masses exponentially suppressed. You could also think of it as a sort of duality conjecture, as in a sense the theory breaks down. A stronger version could be that there's actually a dual theory, fundamental degrees of freedom. Now, there are other sharpened and stronger versions of the distance conjecture, which some we're going to be using here, including from the strongest one, like emergent string conjecture, which is something we see in string theory, where in fact these infinite distance limits either have towers, which are basically weakly coupled string theories, or they're decompactification. So the serpent distance conjecture, or maybe a little bit stronger version of it, where they do fix the coefficient A, what it is based on having a string tower. So knowing, for example, what this is in some canonically normalized scalar field tells us what the tower is in that limit. Okay, so I will focus on, for example, 3 very simple examples to just see what these towers are in those examples. So, for example, we'll know type 2A strong limit, M theory. This is a decompactification. So you have a KK, BPSO 32 with type 1 is an S duality, and you have a light BPS string. And then you have the type 1 prime T duality. KK tower, but that is not BPS. So this is the type of limits we would you're interested in these limits is because when you have BPS states, you have a lot of control. So in principle, especially in 16 supercharges that you don't even have other corrections, you could trace the states. You know they're there, you know what they're doing, and kind of understand their properties. Even though it's not always simple, it's definitely more manageable. Non-BPS states, that's definitely not the case. So it is hard to follow the states from a bottom-up perspective. However, in 9 dimensions, we are a little bit lucky, and we're going to be able to define these non-BPS limits. So we will consider spectrum-specific non-BPS limits in this theory. In these theories, we will show that they mostly decompactify in the sense that it is not that hard to find a direction that actually decompactifies. Then we will show that it actually decompactifies interval, which is what exactly you expect from string theory, but this would be from a bottom-up perspective. And as a result of this, we were able to argue for gate symmetries on 8 branes. So we know from string theory, you put 8 branes together, you get enhanced gate symmetry. But this is a very stringy, in a sense, effect, because we know the UV degrees of freedom. We know that you have strings stretched, you know how to get gate symmetries, but that's not something we know from bottom up. So we will try to understand why something like having 8 brane from, let's say, completeness of spectrum would result in enhancements in gate symmetry. So in 9D, so I will start from my first point of trying to define the non-BPS limits for you. And we have a 9D n equals to 1 supergravity. This has 16 supercharges. And the way we find the non-BPS limits such that all the BPS states are massive. So it is easy to identify the BPS states. We know that the modular space doesn't receive corrections in 16 superchargely, one of infinite distance limits. So what we do is we know the modular space of these theories, and then we also know the kinetic term of the theory specified by some matrix M that has is a combination of this moduli, basically. Now, an infinite in this case, for example, this omega would correspond to also transformation in the lattice. That is because the gauge coupling is controlled by M, and hence the gauge charge also depends on that. So you will also have equivalently some transformation of the charge lattice itself. And this is actually a boost. It's an infinite distance boost that you have, and you can now focus on BPS states, such that this is a BPS condition where M equals to QR. The write the first 10 minus the components of Q, and to extremal states M greater or equal to Q left. And this basically tells us that if I want a tower of massless states, a Q squared should be 0. And doing this transformation basically tells us at the end that the mass of a BPS particle should look something like this. So it scales at infinity in terms of the boost parameter gamma in this form and the dilaton in this form. So these are the BPS particles, at least in that line of boost. By completeness of spectrum, you expect to at least have some states becoming massless. And what you want is to basically make them all massive. So if you make them all massive, and this BPS strings also have a factor of this form, it's 1 over square root d minus 2 phi, you can have a limit such that they're all infinite. And now all BPS states are massive. So anything left massless in this limit is actually a non-BPS state. Okay, so the next step would be, since we're at that limit, to kind of understand what is the probability of having sort of a limit that decompactifies or as a string tower, as we would expect from the different conjectures we discussed earlier. Okay, so the argument, I will summarize a little bit the idea is for the most decompactifications is to firstly look at the basically at their countably many limit has a unique inequivalent direction, so that you would have direction of it and find. So the idea is to firstly have the countably many inequivalence. This we argue this by for gravity. The idea is that if you have some point PA where you have a good description for some string, and to cover this by some countable union of disks. Now you could focus on a region where you can cover this as you can split it in terms of scale. So you can have this scale lambda c, and then you can write the region as a union of these m lambda c states, scales, sorry. And you cover then that region with this, and at each of these you expect basically to have finitely many up to some cutoff, as we know. So as you put them all together and you consider the union of this, you end up with countably many such strings. So this is a sort of a little flavor of our argument. And then we go to have the second. It has a unique and equivalent direction. So in fact, we learned earlier from the sharp and distance conjectures that if we have a tower that is a string tower, the coefficient is -2. That is a string limit. So if you change the direction a bit in this canonically normalized field, in fact, that will not be the leading tower anymore. And since you only have countably many distinct strings, actually the limit you end up with that goes to infinity will be a decompactification. So, okay, so this was a screenshot of why we believe that the theory actually decompactifies. And the next step would be, so we know we are at the non-BPS limit where we have a tower of light states. We have chosen a direction where decompactifies, which we just seen it's not very hard. The third step now is to show to argue where does, from the string theory perspective, we actually expect it to go to massive away on an interval. And we would like to argue basically that this is what happens. So the idea for this, to argue this from the bottom-up perspective, will be as follows. So we are at 9 dimensions, 16 supercharges. So we have a few choices about what to do. You can go to 11 or 10 dimensions. It can come the theory since it's a decompactification. In 11D, you have more supersymmetry, so you definitely need to break supersymmetry. Most of these things, most of the possibilities have some kind of circle inside, so that they actually bring you down a BPS tower, which is not something we want. Now, you could also ask a more general question: can I have something like Campbell, Mobius, etc.? But boundaries, because we need boundaries in order to break supersymmetry, that glued in some non-trivial exotic way, like this. So you have different boundaries. So these kind of things don't appear in string theory, but it would be interesting to understand from bottom up why they also don't appear. So this would be a small aside about this, which we would like to focus about some object in our theory that sort of knows everything or is able to understand the internal geometry. And this is the small instantons. So, and aside from this work here, basically, where they exactly studied the small instantons of the 9D theory. So just before I go to the 9D theory, I should just remind you that in string theory, how we understand them, for example, is you can have fat instantons and small instantons, making them zero size, and you can also expel them from the branes in terms of codimension 4 branes. So basically, you want to understand this structure, you want to understand the moduli space of the small instantons in 9 dimensions, which was done exactly in this work. And as we said, they correspond to 4 branes in this case, and their moduli space is a of 1/g². And in fact, for these 4 branes, we know exactly what the theory is. It's a 5D, it's a BPS object, so half BPS, so it preserves 8 supercharges. So it's a 5D n equals to 1 world volume theory with SU2 gauge symmetry. So the worst type of singularities you have is something like this, while this would give you something worse type of singularity because of the small instanton modular space. So as we saw in general, though, we want a boundary, we don't want S1s, and we want something maybe not as exotic. In 10D chiral theory, you can't have that. Now, in the chiral theory, in non-chiral theory, I'm sorry, you can have an interval. You can again ask me, why can't I have something more complicated where these are boundaries and these are just different domain walls? Why can't I have something complicated? I will tell you again, it's the same story as the small instanton. The small instantons will be able to understand different types of singularities like this, which are worse singularities, and it wouldn't let you have that. So that's great. So that means that this is really only that is allowed here. This is the only thing we can actually have, the 2 boundaries associated to the interval from the non-chiral 10D theory. Okay, so the most general type 2A supergravity is the massive type 2A, where we have added Romann's mass. This is the mass deformation of the classic supergravity type 2A supergravity with this extra term. The equations of motion for the 9-form field here can be written in this form with this nu zero, which is a piecewise constant function. And we know very well, this is really exactly the same computation you would have done in string theory, because it's really a supergravity calculation, where you're able to understand what happens when you turn on that mass. This also couples to the dilaton, so you turn on a non-trivial profile for the dilaton as well. Branes at certain position xi, this corresponds to some change in u0 associated to the tension of 8 branes and the number of 8 branes. Now, the 8 branes themselves are expected to exist because of completeness of spectrum. We assume also BPS completeness of spectrum, since we have these gauge fields. And in string theory, what is the number of branes? I will not assume it here because we want to show how many branes you actually have. But the point is that we get a similar structure as we get from string theory, just from the supergravity. And of course, what you want to do, again, is to be able to match the moduli. So we discussed earlier, you have the 9D moduli of phi and m. M was the full moduli and phi is a dilaton. And now we have the type 1 prime. Type 1 prime refers to the massive type 2A and S1 moduli to supergravity, which depends in these parameters. So that now the positions of the 8 branes, are actually in correspondence with the moduli space of the 9D theory. So that points of enhancement, for example, if you had points of enhancement in the moduli space of the 9D theory of a gauge symmetry, there's something happening also at the position of the 8 branes. And in fact, you can understand much more about this. So because we know the moduli space of the small instantons, then you actually know what the theory is, a 5D n equals to 1 gauge theory with SU2 gauge symmetry. Now, the global symmetry of such theories are classified. We know the global symmetries that are possible. So, and we know the Coulomb range of these theories as well. So that let's have an example. The gauge symmetry in the bulk, this corresponds to one of these global symmetries on the forebrain that we had earlier. And since these are classified, we know exactly what type of symmetries we can have. So these are the possible enhancements that you can have. For example, if this is the interval and this is the profile, then you have, let's say, this type of gauge symmetry here, this type of gauge symmetry here. You have in the 5D gauge theory description. And then as you go to the UV enhancement from the forebrain perspective, where the coupling diverges, you also have the bulk coupling diverging and having an extra enhancement in the boundary over here. So basically now there's a correspondence between, we know that there's a correspondence between the coupling of the bulk coupling and the coupling of the forebrains, which tells you how the symmetry enhancements work. Of course, we want to know more. We want to know how exactly this also occurs in terms of the branes. So we can basically do the following. So we have matched the moduli space of the small instanton, which knows now about the gauge symmetry through the global symmetry on the 5D theory, to the moduli of the 9D supergravity, but we also match the 9D moduli with the position of the branes. And it's very simple to actually see that as you go and approach these enhancement points on the small instanton moduli space, you're actually bringing branes, 8 branes on an interval together, so that you see exactly that happening, that as you bring the 8 branes together, there's a symmetry enhancement. Now, from the bottom up, you don't know why this happens because we don't have the UV description of this, but you have an indication that it actually does happen. That is what is going on. Similarly, you actually get this in the boundaries where you see the physics of the orientifolds, what kind of enhancement you expect in where the orientifolds exists, just from the classification of the 5D gauge theory and SCFTs. Similarly, you can now put a bound on the number of branes since we have a maximal rank for the 9D theories. So each of these have branes associated to them, 8 branes, so that if the total rank is 17, then the maximum is 18 8 branes. Coulomb branch, you get the rank plus 1, 8 branes. So this picture really tells you that knowing certain things about small instanton physics and about the moduli space and about the theory, then it actually tells you a lot about what are the possibilities here and what kind of thing is happening when you bring these branes together, which really from the bottom up, you wouldn't expect to see something like this. Why is there extra master's degrees of freedom leading to these enhancements and stuff? It's not so obvious from bottom up, but we see that the small instanton actually tells you that this should be happening when you bring the positions close to each other because we match the moduli. Exactly. So this is what we studied. So we found the non-BPS limits again. We showed that they decompactify to this description. When you have a non-trivial Romance mass, you can have a nice non-trivial 8 branes on the interval, which can give you all these different configurations. We're able to now rid of gauge symmetry associated to bringing 8 branes together and 8 branes on the boundary, so being on top of orientifolds from bottom up. Now, of course, able to understand in more cases because it is really telling you something about not just about the 8 brane symmetry, but also the non-BPS moduli corner of the 9D theory, which is not something you usually are able to understand very well. So I want to thank you very much, and please tell me if you have questions.
Thanks for the nice talk. So please, everybody who has a question, go ahead.
I have a question.
Yes.
Assuming you're taking a non-chiral theory. What if you take a chiral theory? What's like? Can you do this and do the same analysis, like for example in type?
I'm not taking. There's no 9D. So you mean in 9D there's no chirality? So this is a 9D theory with 16 supercharges. When I talked about chirality, I just talked about 10D. And we know that you just can't put the 10D theory on something with boundaries. So you want to be able to break half the supersymmetry, not more than that.
Okay, thank you.
Other questions? No?